Dear students, we are on the topic solutions in physical chemistry. In the previous session, we had discussed the details of the solubility of gases in liquids, right? And we had discussed Henry's law. In today's session, we will be applying Henry's law, the numerical applications of Henry's law. All right? Now, before we start applying the numericals of Henry's law, applying Henry's law concepts in numericals, let's do a quick recap of what we learned in the previous session regarding Henry's law, or what is the significance of Henry's law. Henry's law is a quantitative relationship between the solubility of a gas in a liquid in terms of mole fraction and the partial pressure of the gas in the solution, over the solution. All right? And so what have you understood? The partial pressure and mole fraction are directly proportional to one another, and you were introduced to a Henry's law constant. Okay, so we will be using that formula to solve these numericals. So here is the first numerical. The partial pressure of ethane over a solution. So ethane is the gas over a solution containing 6.56 into 10 to the power of minus 2 grams of ethane is 1 bar. So from the first sentence, what information has been conveyed? You've been provided with the partial pressure of ethane, right? The partial pressure of ethane over the solution, which is 1 bar. You're also provided with the mass of ethane, right? Next, if the solution contains a different mass, 5 into 10 to the power of minus 2 grams of ethane, then what will be the partial pressure of the gas, right? So let's quickly write down the mathematical statement of Henry's law, which is partial pressure is equal to Henry's law constant, which is a constant of proportionality, into the mole fraction of the gas in the solution, dissolved in the solution. So P is the partial pressure of the gas over the solution, and this is the mole fraction of the gas in the solution, right? And this expresses the solubility of the gas in that particular solvent. All right? Now, in the first statement, you are provided with the mass of ethane, correct? So let's first find out so we can find out the number of moles of ethane. Okay, now we are not aware of the number of moles of the solvent. So let's assume it to be X. So if you are able to, and you know the partial pressure, which is 1 bar, correct? So let's make some assumptions and substitute in this formula. And from this, the only unknown factor is the Henry's law constant. And you know that at a given temperature, Henry's law constant will be the same. All right. So whatever value you determine for Henry's law constant can be used in the next situation where the mass is different and you have to find out the partial pressure of the gas. So this is the context or the background information regarding this numerical. So let's first start with the determination of the mole fraction of ethane. To find out the mole fraction of ethane, first we find out the number of moles of ethane, which is mass over molar mass. The mass is given as 6.56 into 10 to the power of 6.56 into 10 to the power of minus 2, which is 0.0656 divided by the molar mass of ethane is 30. Okay, so what is this value equal to? 0.0656 by 30 would be approximately 2.2 into 10 to the power of minus 3. Okay, so that is the mole, that is the number of moles of ethane. We are not aware of the number of moles of the liquid, the solvent. So let the number of moles of the solvent be equal to X. Okay, so we have this information. From this, we can write down the formula for mole fraction, which is the number of moles of ethane divided by the total number of moles of ethane and the solvent put together, right? So that is our next step. Therefore, the mole fraction of ethane would be equal to number of moles of ethane, which is 2.2 into 10 to the power of minus 3 divided by the number of moles of ethane plus the number of moles of the solvent, which we represented as X. Now, in solutions where a gas is dissolved in a liquid, the concentration of the gas, the solute, will be much less compared to the amount of the solute, right? Sorry, amount of the solvent. Most of these solutions are dilute solutions. So, the denominator 2.2 into 10 to the power of minus 3 plus X is almost equal to X, because this is a very small amount. Alright, so the mole fraction of ethane can be modified as 2.2 into 10 to the power of minus 3 divided by X. So that is the mole fraction of ethane, right? And what is the partial pressure when the mass is 6.56 into 10 to the power of minus 3? 1 bar, right? So from this we can find out the value of the Henry's law constant. The value of Henry's, the formula would be partial pressure divided by the mole fraction of ethane. Partial pressure is 1 divided by the mole fraction would be 2.2 into 10 to the power of minus 3 divided by X. So X is here, right? So basically you will get the Henry's law constant as X divided by 2.2 into 10 to the power of minus 3. Correct? So that is Henry's law constant. So we will use this Henry's law constant value, okay, into the next situation where the mass of ethane is 0.05. So next we find out the number of moles of ethane. The mole fraction is therefore number of moles of ethane by X. Same situation, because in such a solution the amount of solute is far less compared to the amount of the solvent. Right? And we substitute this value of KH and proceed with the calculations. So now we find out the number of moles of ethane, which is in the second situation, number of moles of ethane is equal to mass over molar mass. So this would be, molar mass of ethane is 30. So this would be approximately equal to 5 by 30, 1 by 6. So this will be equal to 1.67 into 10 to the power of minus 3. Alright. So now what is the mole fraction of ethane? We make the same modifications as in the previous situation and we get the mole fraction of ethane as number of moles of ethane divided by the total number of moles of ethane plus number of moles of the solvent. We are considering the number of moles of solvent to be X, which is much larger than the number of moles of the solute ethane, and therefore the denominator is X, right? So now we need to find out the value of the partial pressure. So partial pressure is equal to Henry's law constant, which we got as X divided by 2.2 into 10 to the power of minus 3. X divided by 2.2 into 10 to the power of minus 3 into the mole fraction, and the mole fraction is 1.67 into 10 to the power of minus 3 divided by X, right? X gets cancelled and the value of the partial pressure would be 1.67 into 10 to the power of minus 3 also gets cancelled. So it is 1.67 divided by 1.67 divided by 2.2. So this has to be calculated. Alright, so this is how you find out the partial pressure, and this is not a direct application. This question involves two situations at the same temperature. So when temperature is constant, the Henry's log value also will be a constant. KH will also be a constant. So that is what is to be kept in mind here. All these calculations are presented neatly here. So let's quickly do a recap of the steps that we used in the solution of this particular question. So first we found out the number of moles of ethane. We got 2.2 in 10 to the power of minus 3. Let the number of moles of solvent be X, and then the mole fraction was this, and we assumed X to be very large compared to this, and hence the denominator was X. The pressure of ethane is, the partial pressure of ethane over the solution is 1 bar, right? Next, we use this formula to find out KH. Okay, now the mole fraction, we have made a modification here. The mole fraction of ethane, we removed, the numerator has to be 2.2 into 10 to the power of minus 3 plus x was modified as just x, right? So we got x divided by 2.2 into 10 to the power of minus 3. So that is the Henry's law constant in the first situation, and the second situation where temperature is maintained a constant, we substitute that value and get the value of the partial pressure. So we again found out the number of moles of ethane, 0.05 divided by 30, which is this value, right? Let the number of moles of solvent be x. We know the value of KH from the previous calculation. We substituted everything in this formula, correct? And we arrived at the final value for the partial pressure when the mass of ethane is 0.05 grams of 0.05 grams. So what is the partial pressure equal to? 1.67 divided by 2.2, which is 0.76 bar. So that is the final result of our calculation. So we got the answer as 0.76 bar. That is the unit of pressure used. Okay. Now let's move on to the next question. Henry's law constant for oxygen dissolved in water is 4.34 into 10 to the power of 4 atmospheres at 25 degrees Celsius. So let's make a note of that information first. That is equal to 4.34 into 10 to the power of 4 atmospheres. Alright, next, if the partial pressure of oxygen in air is 0.2 atmospheres, so partial pressure is equal to 0.2 atmospheres. So we have the Henry's law constant and the partial pressure. So from this you can immediately find out what the mole fraction of oxygen. But that is not the question. The question is, calculate the concentration of oxygen gas dissolved in water in moles per liter. Moles per liter signifies what? Molarity, right? So you will get the the concentration you can directly solve as mole fraction, and then you have to convert it to molarity. We have solved questions in the past where we have related different concentration terms, and that is what we have to apply here. Alright, so let's continue with our discussion. Let's quickly write down what is the value of the mole fraction of oxygen gas. So mole fraction of oxygen gas would be partial pressure divided by Henry's law constant, which is 0.2 divided by 4.34 into 10 to the power of 4, right? 4.66 into 0.2 by 4.34, so 2 by 43.4, okay, and 10 to the power of 4, so this becomes 10 to the power of minus 6. So approximately 4.66 into 10 to the power of minus 6, right? So you notice how small the amount of the concentration of oxygen is in the solution, all right? Next, okay, so we have got the mole fraction of oxygen. Now it is dissolved in water, correct? Now we need to find out, so let's now write down the formula for molarity. So we have expressed the concentration of oxygen in terms of mole fraction. We want the concentration of oxygen in terms of molarity, and the solvent is water. Now let's write down molarity is equal to, M is equal to number of moles of the solute, right, divided by the volume of the solution into 1000 if the volume of the solution is in milliliters. Okay, now this is the formula for molarity. We found out the mole fraction of oxygen as 4.66 into 10 to the power of minus 6. That is the mole fraction of oxygen, right? And we need to substitute here the number of moles of oxygen. So we know the mole fraction. So mole fraction is equal to, mole fraction of oxygen is equal to number of moles of oxygen divided by number of moles of oxygen plus the number of moles of water, the solvent. Correct? We need to find out the number of moles of oxygen here, right? But in order to find out the number of moles of oxygen, we need to first find out the number of moles of water. We already know the mole fraction of oxygen. Correct? Now we can make a small modification here. Since the number of moles, since it is a very dilute solution, the amount of oxygen gas dissolved in water will be very small compared to the amount of the solvent water. So we can modify this formula as number of moles of oxygen divided by number of moles of water. So now our task is to find out number of moles of water. We have 1 liter. We need to find out the concentration in moles per liter in 1 liter of the solution. So V is 1 liter of solution. But because the solute is a gas, the amount of the gas dissolved in water is very small. And hence, the volume of the solution can also be taken as the volume of water. So we have 1 liter of water. So that is our next calculation. So 1 liter of water, so volume of water is equal to volume of solution, which is 1 liter, and that is equal to 1000 milliliters, right? 1000 milliliters. Now, 1000 milliliters implies what mass of water? 1000 grams of water, right? Because density of water is 1 gram per milliliter. So mass of water, so now we have the mass of water, which is 1000 grams, right? So immediately we can find out the number of moles of water, which is mass of water divided by the molar mass of water, and that is equal to 55.5. So that is the number of moles of water. Now we can substitute this value into the formula we wrote earlier, which is mole fraction of oxygen is equal to number of moles of oxygen divided by number of moles of water, right? So now we get the number of moles of oxygen. Once you calculate the number of moles of oxygen by multiplying these two numbers, right, that is substituted in the formula for molarity. Okay, so number of moles of oxygen is obtained by multiplying the mole fraction of oxygen and the number of moles of water, and you get 2.55 into 10 to the power of -4. So that is the number of moles of oxygen. Substitute that value in the molarity formula. So number of moles of oxygen, 2.55 into 10 to the power of -4 divided by volume is 1 liter. 1 liter. Therefore, the molarity of the solution is 2.55 into 10 to the power of -4. So this is the answer to the concentration of oxygen gas dissolved in water in terms of moles per liter. All right. So these were the steps, a quick recap of all the steps that we used to solve this particular question. First, we applied this formula to determine the mole fraction of oxygen gas. You were given information about the partial pressure and Henry's law constant to find out the mole fraction, and the mole fraction that you got was 4.6 into 10 to the power of -6. So once that was obtained, we started with the molarity formula to find out how to convert mole fraction to molarity, right, or moles per liter. Now, this is the formula for molarity. Now here, N stands for the number of moles of oxygen, V stands for the volume of the solution. Volume of the solution is equal to volume of water because oxygen gas is found in traces, right? So 1 liter of water contains 1000 grams of water. If this is the mass of water, then the number of moles of water would be 55.5. So now we have the number of moles of water. We have the mole fraction of oxygen. We can find out the number of moles of oxygen by making one more modification, which is as the number of moles of oxygen gas in water is very small compared to that of the solvent, the denominator would just be number of moles of water. So this is the formula that we have to use further for our further calculations. So from this, the only unknown factor is the number of moles of oxygen. We know the mole fraction of oxygen, we know the number of moles of water, and we get the number of moles of oxygen as 2.55 into 10 to the power of minus 4. This has to be substituted into the molarity formula. Volume is 1 liter. So there's no need to multiply by 1000. And therefore, the molarity is 2.55 into 10 to the power of minus 4. Or the concentration is 2.55 into 10 to the power of minus 4 moles per liter. So these were two different kinds of numericals where Henry's law was applied.